Welcome back to everybody. We are up to the last lesson of the first half of Unit 4. So this will actually be the last lesson of Semester 1 of Algebra 2A. So let's take a look at the examples since there are no new lesson notes. Carbon-14 is used to find the age of certain artifacts and fossils. It has a half-life of 5,730 years. This means that if an element has carbon-14, it loses half of it every 5,730 years. Number 1. At a certain time, a fossil has 3 picograms of carbon-14. Write the equation for the number of picograms of carbon-14 per 5,730 years. So I'm going to use my exponential, in this case, decay formula since it's a half-life. So my initial value here is going to be 3. Okay. My decay factor is going to be a half because it's a half-life to the power of x. Okay. And then it's important to realize that x is not number of years. X in this case is the number of 5,730 year time periods. So this is my answer to number 1. Number 2, at a certain time, a fossil has 3 picograms of carbon-14. Write the equation for the number of picograms of carbon-14 per year this time. So the question is, if I have number of years, what do I have to do to the number of years in order to find the x value? So for example, if I wanted to find the number of picograms after 5,730 years, I would plug in x equals 1 because that's one 5,730 year time period. Okay. The point is I would take the number of years and divide it by 5,730. If I had, and I'm going to grab a calculator here from my phone. Okay. If I had 11,460 years, if I wanted to figure out the number of picograms after that many years, I would have to take that and divide it by 5,730, and that would give me an answer of 2. So I would have to plug in 2 for x in that situation. Okay? Let me do one more. Okay? If I had, and again, I'm using a calculator on my phone, 17,190 years, I would have to take that and divide it by, again, the half-life, and I would get, in that case, 3. So 17,190 years is 3 5,730 year time periods. So the key in this case is I'm taking the number of years and dividing it by 5,730. So my equation is going to be 3 times 5 to the power of, and I'm going to use t this time, t divided by 5,730, where t in this case is now number of years. So 3 times t to the power of t over 5,730. So now, to do number 3, to complete the table, all right, if I want the number of the mass after 1,910 years, I can plug in 1,910 in for t. So let's go ahead and do that. Okay, so it's 3 times 0.5 to the power of 1,910 divided by 5,730. right? All right, and the mass is going to be, I'm just going to round that to 2.38. So the mass is 2.38. And then if I want to figure out the number or the mass after 5,730 years, I can plug in 5,730 in for t. So let's do that. 5,730 in for t, and my mass is going to be 1.5. Okay, so that's the answer to number 3. Okay. Number 4, it's a different situation. I'm going to do this one down here. A scientist models the number of grams of a radioactive substance with the expression 10 times a half to the power of d over 6, where d is the number of days since the sample was measured. A. After how many days has half of the substance disappeared? So in other words, what's the half-life? Okay. Well, in this case, remember it was t over 5,730. So that 5,730 was the half-life of carbon-14. So the half-life ended up in the denominator. In this case, the denominator is 6. Okay. So in this case, the half-life is going to be 6, and I think D stands for days. So the half-life in this case is 6 days. The key is the denominator of the exponent is your half-life. Okay. B, after 15 days, will there be more or less than 1 gram of the substance left? So what I'm going to do is I'm going to take my equation and I'm going to plug in 15 for D, because D, remember, is the number of days. So I need to calculate 10 times a half to the power of 15 over 6. So 10 times a half to the power of 15 over 6, and I get 1.77 grams. Okay? So to answer the question, after 15 days, will there be more or less than 1 gram of the substance? There will be more than 1 gram, because 1.77 is obviously greater than 1. Okay? And that is it for this lesson.